Welcome you all to today's video lecture. Today we will look at system response with the addition of poles and zeros. So, system response with additional poles. So just overview what we did till now. We assume that we have second order system. Okay, so this is our second order system, and for this particular system we know that we have a system response, and response is has some properties in it that includes so if I draw the response to the step input, so step response start from here and do something like that. So this is your y of t, this is your time t, and you do have some rise time, settling time, and so on. Okay, now this what we know, and similarly this is for second order. Before that we discussed first order system, and for first order we assume that we have s plus a. So this is a first order system. That system, so the main idea is to that if we look at the step response, we have something like that. So one, okay. So the basic idea here is that, so these are basic two response. So this is for second order, this is for first order. Now we know the properties. So what now question is, what about higher order systems? Or you can say that what about more than second order system? So this is the basic idea that we need to look at. So that's why we discuss what happened if we add some poles in the system. So before that we have to look at basic things here. So one thing, when we discuss S-plane, and we said that we have imaginary and real part. So this is our S-plane. So the main idea we discussed that for stable system we defined dominant poles. We defined concept of dominant poles. So what are dominant poles? So dominant poles actually the second order poles that are near to the origin and overall response follow it due to slow convergence. So the main idea is that because dominant poles are those poles that are near to the origin. For example, if these are two poles, so these poles are dominant poles. If these are other poles, so these are non-dominant poles. These poles are the dominant poles. Okay, so the main idea is the main shape of the response is based on these poles, dominant poles. So the overall response shape is due to dominant poles. So this is the basic idea. So from where we can discuss that if we add some pole, so the main idea, the overall response is same, only it will affect as your poles is more near to the dominant pole. So when it is near to the dominant pole, so your response will vary. So for example, to understand this concept, let me consider an example here. So example, in this example we assumed different cases. Okay, for example, we have first case, these are dominant poles, and we introduce a pole here. So this is case 1, this is your geometric axis, alright. So this is the real part. Similarly, if we look at the case number 2, where we try to put dominant pole further away and the new pole further away from the dominant poles. Okay. So this is case number 2, and case number 3 is the one if we don't have any other pole here. Okay, no dominant pole. So this is case number 3. So we have 3 cases and we want to discuss how they behave. Now if I plot a response here, I assume this is the time t, and I look at the step response. So this is y of t. Okay. So let me assume this is the behavior of case 3. Okay, where we have only 2 dominant poles. Now if we look at case 2, because case 2 is further, this pole is further away from the dominant pole, so it doesn't affect shape much. So for case 2, let me change the color. For case 2 we have almost same shape. Okay, so this is for case 2. Now the last one is the case 1, where we have a very much near the dominant pole. So in that case, case 1 is much different as compared to case 2. So so case 1 maybe behave differently. Okay, so it can have very different behavior. So this is case 3, sorry, case 1. So the main idea here is you have to look at is that basically as you are more near to the dominant poles, you can affect the shape. Otherwise, if you are further away, because due to force convergence, so it doesn't affect much. Okay, now we move to next thing, that is what happened if we are adding some zeros to the system. So system responses with zeros. So now here the main idea is that if we introduce some zeros, okay, to the system, Now how it affects the overall phenomena. So for example, if we have a second order system, okay, assume that we have a second order system look like this. G of s is equal to 1 divided by s plus 1 plus j 2.828 times s plus 1 minus j 2.828. So this is the system. Now here if we add zeros, so if we add zeros at z equal to you assumed you add 0 at -3, then at -5 and at -10. So let's look how response look like. So if I give step input to this system, so here the interesting thing is that when we add 0 to the system, it doesn't affect much. So for example, if no zero response is something like this, so we call it no zeros. Okay. Now if we look at the next one, where 0 is at -10, -10, which will give almost the same response. So this is at z equal to -10. So as we come near to the dominant poles, so this response behaves like this. Okay? So at this is at z equal to -3. So the main idea is as you come near to the what you say 0, it will affect the response. Otherwise 0 didn't affect much to the response of the system. Now the interesting thing that we need to know is response of the 0 when 0 is at. So there are two possibilities that you can add 0, either 0 at left half plane, so I am talking about S plane, or 0 at right half plane. So this is right half plane. So this is S plane. Now let me change the color here for right half plane 0. So I use a red color. So that now let's look at the response, how both response vary from each other. So if this is my output and I am looking for step output, okay, so this is the time. Now if I am looking the first one with left half plane 0, so this is the response, first one. Okay, now this is when we have this situation that we have left half plane zeros. Now interesting thing is when we have right half plane 0, so this response, instead of going in this direction, it will start going in opposite direction first, then start to go in this direction. So this make this response a bit slow. So this is because of right half plane. So right half plane always response will start in other direction then come to back. So this is when we have right half plane 0. So the main idea is that if you have this type of thing, so this means that this is non-minimum phase system. So this is minimum phase system. So when you have a 0 at left of plane, so this means that your system is a minimum phase system. It will start from 0 and go in that direction. But if it is non-minimum phase system, in response it will start in opposite direction and then come back and move in other direction. So this is the basic idea, and when it is goes in the opposite direction, what happened, the overall system response is slow, because it will first go in opposite direction then come back to it. So this is very, very important thing that we must know. Okay, now another topic that is related to response need to be done is effects of nonlinearity upon time response. So it's very important. You have to look at the response of the system and you identify how response look like. So if you remember, we discussed different nonlinearities that we have in the system. So first one was, if you remember, was the saturation. So saturation. So in saturation, so what happened, if you have a response, so how response look like without saturation and with saturation. It will start with, so if it is saturated it will stuck here, but if it's not saturated it will go where it want to. So this is without saturation, this is with saturation. So means that the response is stuck in between. So this is the effect of saturation. Now we look at the next effect, that is due to the dead zone. So if you remember, in dead zone we have a difference, that there was some point where you apply the input to the system, but it's not possible to do it. Okay? Now in dead zone, what happened, if I plot the response here, so dead zone, if it is without dead zone, it will perform like that. Okay, so this is without dead zone. Now if I plot with dead zone, we start here and then move in this direction like this. So red is with dead zone. So if you remember what happened in dead zone is that there is some time when you apply the input, but you are not due to the constraint, input is not applied to the system, so you don't find any output. So that's why we have less amplitude and move sluggishly as compared to without dead zone. Now the last one, if you remember, that was backlash. Okay, so for backlash, if I look at the response, it will move, for example, in this manner. Due to backlash, there are some point and there's some difference where you didn't find any output. So in that case, let me write it without backlash. So in backlash it will start here, and then it will saturate it for some time. Then when contact is again made, it will start, then contact is lost, then again saturate it, and again move it, and then saturate it, again move it, and then saturate it. So this is with backlash. So this is the basic idea. Now these are the types that affect the response. So, and the last one is Laplace transform solution to state equations. So if you remember, state space representation is written as x plus bu, y is equal to cx plus du. This is our state space equation. Now if I apply the Laplace on that, after applying the Laplace, if we apply the Laplace, so it becomes s x of s, okay, minus x of 0 is equal to a x of s plus b u of s. Similarly for next one, y of s, c x of s plus d u of s. So this is the basic when we apply the Laplace. Now after that, if we want to find, we can write this x at one side, it becomes this for first equation, okay? Or in other words, we can calculate x of s is actually si minus a whole inverse x of 0 plus si minus a whole inverse b times u of s. Okay. Now if I want to calculate x of s, so it is equal to adjoint of si minus a whole determinant of si minus a x of 0 plus b u of s. So now as we know that y of s is equal to c x of s plus d u of s. To calculate the transfer function, that is y of s divided by u of s. For that we just have to plug in the values here. Y of s equal to c therefore transfer function x0 is equal to 0, so it becomes adjoint si minus a whole divided by determinant si minus a time b plus d divided by u of s. So this is the transfer function we are getting. Or we can write it can be written as determinant of Si minus A, that is equal to C times adjoint of Si minus A times B plus D times determinant of Si minus A. So y of s divided by u of s, the important point here what we get is that adjoint of Si minus A times B plus D times determinant of Si minus A whole divided by determinant of Si minus A. So what we learned is that the ratio of output to input is known as transfer function, normally represented by g of s, but the important point here is that we need to know the determinant denominator. When I put equal to 0 give us the poles of the system. So determinant Si minus equal to 0 would actually give us the poles of the system. So the main idea here is we find the eigenvalues and that are actually the poles of the system. Now this is what we have for converting into the transfer function. Now the next thing that we have is time domain solution. Solution of state equation. So the main idea is to solve the equation we need the time solution. So how we do that? The time solution that we can calculate easily calculating inverse Laplace of the transfer function. So if I want to calculate x of t is equal to exponential at x of 0 plus we have integral that 0 to t exponential minus a t minus tau b u of tau d tau. So this is the equation where we can calculate the response, or we can say that test for state variable we call it phi of t x of 0 plus we do the integration, but here we have a phi of t minus tau b u of tau d tau. So this is the equation that we can get when we do the inverse Laplace. So now we are not going in further detail. We will come back to this later in the course, but this is what we get when we have time response of the system. Now I will stop here. We will continue next. So before concluding, so you have to know that we discussed basically first order system, and second order system. Then for higher order we say that we have dominant poles that tells us about the response. First order basically we discuss time constant, we discuss rise time, we also discuss the steady state. Here we discuss overshoot, rise time, settling time, peak time, these things in second order system. Then we further uh, divide it into based on the zeta values. So that can be critical damp, undamped. We have undamped, we have critical damp, we have overdamped, we have underdamped responses the system. So this is what we look at, and then we see that what happened when we add the poles. So the main idea is that overall response is based on the dominant poles. What happens 0 0 doesn't change much, but if it is in the left of plane, but if it is in the right of plane, it will give a significant change in the response, that your response is starting in opposite direction, come back to the original direction. So the main idea is that when you have a 0 on the right of plane, you can say that this is a non-minimum phase system. Otherwise, if it is in left of plane, then you can say that this is minimum phase system. So here we will stop today. Thank you.